I'm going to say something about the energies of orbitals. The energies of the different orbitals in an atom depend on a couple of things. First, they depend on the nuclear charge, and specifically the larger the charge, the lower the potential energy. And the lower the potential energy, the more tightly bound the orbital is to the nucleus, and the smaller it is. And it also depends on something called shielding. And the shielding is due to other electrons preventing an electron from seeing the full positive nuclear charge. And we refer to something called an effective charge, and that is the actual nuclear charge minus the shielding effect. So for example, for magnesium, the magnesium atom, the 1s electrons, the first two electrons in magnesium, they're at the very lowest energy. They see a nuclear charge of 12. That makes them much, much lower in energy and much, much smaller than the equivalent electron in hydrogen. For electrons in the second shell, the effective nuclear charge is approximately 10. This is not exact, but that comes about because we have a full nuclear charge of 12, and between the electrons in the second shell and the nucleus are those two inner electrons. So the effective nuclear charge then becomes 10. This is not exact for two reasons. First of all, the shielding is not complete. The inner electrons don't completely shield the outer electrons from seeing the full charge, and then also the electrons in one shell partially shield each other. But this gives you a rough idea of how the effect works. And then for the electrons in the third shell, there's two of them. The nuclear charge that they see is the 12 for the nucleus, and then the 10 electrons that lie closer to the nucleus than those two electrons. Those are the electrons from the first and second shell, giving me an effective nuclear charge of 2. That makes that orbital, specifically the energies of the orbitals. Remember, the energies of the orbitals are much bigger than the orbitals in the first. They represent the amount of energy it takes to remove that electron in energy. So if we look at the 1s orbitals, that's the blue here. We see for hydrogen, helium, lithium, beryllium, they go downward in energy considerably because of the increase of nuclear charge, and those electrons are not shielded from the nucleus. When I get to so hydrogen and helium, I can see that this is about the ionization energy of hydrogen, and this is about the ionization energy of helium. The ionization energy is actually the positive equivalent of this number. Now for lithium, lithium has 3 electrons, but the first shell is filled at 2 electrons, so the second electron goes into the 2s orbital shown here. And notice that lithium would have a much lower ionization energy than hydrogen and helium. And then beryllium, both sets of orbitals get drawn in tighter to the nucleus. And we continue that plot through the second row to helium. Notice what happens to the 1s electrons. They become much lower in energy. Remember that chemical energies, bond energies, ionization energies, and so forth are all within about 1,000 kilojoules per mole, and it takes much, much more energy to remove these electrons. So they tend to become unimportant chemically. The 2s electrons, notice we're going down in energy as we go across for the 2s electrons for these elements. But then we start filling the 2p subshell shown in yellow. And again, we go down in energy as we go across a row of the periodic table. So the ionization energy effectively goes up as I go across a row of the periodic table. But when I get to a new row, it drops considerably because I'm filling a new shell. And this shows the plot extended through all the way up to calcium. Notice the 1s electrons have become the blue bars for the 1s electrons have become so negative that it's not convenient to show them on the graph. The 2s electrons, 2s and 2p, the electrons in the 2 shell. Here it is for neon right there, and then for sodium and subsequent elements, notice how they get drawn in closer to the nucleus, and they become inner electrons very far away from that 1000 kilojoule mark, and they become unimportant. But then I start filling electrons in the 3 shell, 3s there. And for some reason, I think on this plot, the 3p, well, it should be that. I don't think the 3p is very visible on this plot for some reason. And then I show for the last 2 elements, potassium and calcium, I start seeing the 4s electrons, which are barely visible here. Those are comparatively much easier to remove, and then these therefore have a much lower ionization energy than the other elements shown.